So, completely away. Thank you. So, this lesson is kind of going to be split into two parts. We're going to talk a little bit about asteroid impacts, and then we'll talk about black holes. Suppose a 45,000 kilogram asteroid, not that big an asteroid, is traveling at 5.67 times 10 to the fourth meters per second at a distance of 1.2 times 10 to the seventh meters from the center of the Earth. Justin, what's A asking me to find? Am I going to go like this? Work equals change in, don't write this down, plus change in kinetic. Tell me why I would not do that. It's really stupid obvious. What did the question ask me to find? It did not say how much work. I will make sure if I want you to do a work question, I will include the phrase how much work. Sometimes in the homework, they're going to be a bit vaguer or on the ultimate review, but in my quizzes or my tests, if I want you to find the work, you know I'm going to ask you to find, spoiler alert, the work. What did this want me to find? Can I go gravity is what's pulling me in a circle? If I'm crashing into the Earth, am I in a stable orbit? Let's not do that. Every year I see some kid that starts out, oh, I can find V, or they're going to find V orb and go a half mv orb squared. No, 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 no. Don't be going gravity is what's pulling me in a circle. We're crashing into the Earth. This is not a stable orbit. So what approach am I going to use? So you're just saying I go a half mv squared? I disagree. This is going to take some writing. What approach am I going to use? Not work equals change in plus change in, not gravity is what's pulling me in a circle. Let me be a bit more obvious, Justin, in this question. So you can imagine, I'm going to draw, don't write this down. Here's what we have. Asteroid coming in and hitting the Earth. Is there a change in height? Is there going to be a change in speed? Is there a yucky curvy force? What should I use? No, you just said work, and I just told you we're not going to be finding work. That's a bad, what? Conservation of energy. And the reason I'm being so nitpicky is common mistakes that I see kids start out with a completely wrong approach. And the problem is if you do that, there's not many part marks I can give you. Oh, thank you for finding the work, not what I asked. What's the law of conservation? Oh, it's on your sheet, but I've memorized it. It's initial plus initial equals final plus final. And then I always ask myself, are any of these zeros? Oh, potential energy, that's zero when you're on the ground, right? Don't say yes. We're going cosmic. Where is cosmic potential energy zero? All the way out at infinity. Read the question. Are we starting or ending at infinity? Justin, you're going to say no. Rats. Oh, kinetic energy would be if we were at rest. Are we starting at rest? No. Are we ending at rest? No. We're hitting the earth with a lot of kinetic energy. Nothing cancels here. But what do they want me to find? I guess I would at least minus that over. So I'm going to have this KE initial plus PE initial minus PE final. And then, Justin, if you don't mind, I'm going to put the KE final over here by itself because that's where I'm used to seeing it. And now I'm going to expand it with the equations. So it's going to look like this. KE final equals a half mv initial squared plus mgh, no, negative big G, big M, little m over R initial minus negative big G, big M, little m over R final. If they had said find the impact speed, and if I had written a half mv initial squared right here, the little m's would cancel. But right now, because they want the kinetic energy, the little m's are not going to cancel. I mean, the only tweak I can do, what's a minus minus the same as? And I'm going to start going to numbers now. I'm going to do each one of these separately, write them down to 5 sig figs, and then add them up. But first of all, because there's so much room to make typos, I am going to carefully write out the numbers. I've scrolled down. It's going to be 0.5. What was the mass, little m? Was it 45,000? Okay. Not that big as asteroids go. What was its initial speed? Don't forget the squared. And then plus negative, that's just minus. Do we all know what big G is, or do I need to write it out? We're good. Do we all know what big M is? That's mass of the Earth. I will put the 45,000 there. What's our initial? I'm starting in outer space. So what number did I give you? Where am I starting? Is that a radius, or do I need to add the radius of the Earth? In other words, is that a height or is that a radius? Can you read me the whole phrase with that sentence, with that number? Keep reading. So I'll ask you again, is that a height? That's a radius. So I don't need to add the radius of the Earth. What was the number? Sorry, Justin. 1 point. Not plus 6.38 times 10 to the 6th. This time they gave it to me from the center of the Earth. Plus same thing times same thing times same thing. What's our final? Surface of the Earth. And so, Ragev, I'm just going to write our Earth. I'm going to do each of these terms separately. Not worth trying to do this. If I tried to do this in one step, I'd almost certainly make a typo, Luke. Not even going to try. But I would encourage you, all of you, to get out your calculators and try this, because some of the big issues here are calculator mistakes. 0.5 times 45,000 times 5.67 times 10 to the 4th squared. For the kinetic energy at the beginning, I get 7.2335 times 10 to the 13th. Double check. Yes, Sophia nodding. Anybody else? Yeah, 7.2335. 7.2335 times 10 to the 13th. Takeaway. .67 scientific notation, -11. 5.98 scientific notation, 24. 45,000 divided by 1.2 times 10 to the 7th. Squared on the bottom here. Nope. Be careful. Know when you're squaring the R and when you're not. Here we're not squaring the R. Gonna check for typos. Can you all confirm for the second term? Do you get 1.4957 times 10 to the 12th? I got one confirmation. I did a couple more. I got two. Give me one more, because it is easy. Yeah, okay. Because this is heavy duty typing. 1.4957 times 10 to the 12th. And then plus. Now, the nice thing here, Keaton, is what? I can just backspace and edit. In fact, the only thing I need to change is the denominator, 6.38 times 10 to the 6th. I think that's the radius of the Earth. And I get 2.8133 times 10 to the 12th. Anybody confirm? I got one thumbs up, two thumbs up. Okay. 2.813. And now I'm going to add these together. How much kinetic energy is this asteroid going to have when it plows into the Earth? It's going to be 7.2335 scientific notation button 13 minus 1.4957 scientific notation button 12 plus, I can use my answer button here at least. And I get, Justin, did you get 7.37 if I round off properly times 10 to the 13th joules? Yep. I got one thumbs up. I got Sophia. I got Carson. 7.37 times 10 to the 13th joules. Is that a lot of energy? I wanted to put it into some context. So I looked up the amount of energy in the first atomic bomb ever dropped, the one that was released over Hiroshima. And that is 6.3 times 10 to the 13th. This is basically a small atomic bomb going off. Would you want to be in the vicinity? No, no, no. And this isn't that big an asteroid. Just for giggles, let's figure out how fast it's hitting the ground at. So if I had asked that right away, instead of starting with part A, Declan, where I asked you for the KE, if I had said go straight to the velocity, I would have done all this anyways, and then here is where I would have replaced the KE with a half mv squared, and then go, oh, well, you know what? I would have gone like this. KE equals a half mv squared. Kevin, not Kevin, but Kevin, how do I get the v by itself? I'm going to go times by 2 and divide by m. Okay? So I'm going to go 2 times the kinetic energy divided by the mass, and then what? Square root. So it's going to be the square root of 2 times my answer button divided by, was the mass 45,000? Double check me, but I've gone to the next. Is that right? Okay. So I'm going to go answer button, 2 times answer button divided by 45,000 square root. And it's coming in at 57,200 meters per second. Well, actually, I knew it was going to be coming in faster than escape velocity from Earth, which was 11,200 meters per second, because it's going to pick all of that up and whatever kinetic energy it happened to have when it entered our solar system, which in this case was considerable. Okay. Now, coming in this fast, some of it would start to burn up in the atmosphere, parts of it would blow up in the atmosphere, but an asteroid this size, a big chunk would make the ground. Have we been hit by asteroids before? Sorry? We think so. What's our evidence for that? Because we weren't there. Just saying. First of all, we're pretty sure we know where the crater is. It's a huge crater in Mexico. And then also right around the time we think it happened, when we dig through strata layers anywhere in the Earth, right when we get to that time, all over the planet, there's a very thin layer of iridium, which we think was what the asteroid was made up of when it exploded. That would have been sent into the atmosphere, gone all over the Earth, and kind of fallen down like some weird snowfall. So we have this unexplained everywhere, right about at the same strata when you dig down to roughly the same year on the Earth, this iridium coating. It's our best explanation. So asteroid impacts have happened in the past, both when the dinosaurs happened. There was one that exploded over Russia in the 1910s in Siberia. As far as we know, no one died, but there's this 500 square kilometer area where all the trees got flattened. So our best explanation is we think it exploded in the atmosphere and flattened all the trees. And you all know about Apophis, the asteroid that's due to hit us in 2034, right? You know about Apophis, the football stadium-sized asteroid. You don't know about... Do you not... Are you... Wow, put your pencils down, look up. I heard one person said they knew about it. You should know about this. You should be scientifically literate. Let's talk about Apophis.
Yes, in the middle. Just speak up, and you won't need the microphone.
Hi, I'm Daisha. You spoke about an asteroid coming towards Earth.
Well, she didn't forget that asteroid, did she? She didn't forget the asteroid. So you want a quick update on the asteroid. There's an asteroid the size of the Rose Bowl,
Football stadium.
headed towards Earth. It's called Apophis, named for the Egyptian god of death and darkness. Now, it wasn't coincidental that it was named that. When this asteroid was discovered in December 2004, its trajectory was calculated based on a short segment of its orbit, because you look from one day to the next, it's in a new place in the sky. These folks are moving. Once you saw that its trajectory would intersect the orbit of Earth, you don't name that asteroid Bambi or or Tiffany, right? You're going to give it a name befitting its...
Some sense of gravity.
Yes.
No pun intended.
Yes. That pun was surely intended. The reason why you never heard of it, perhaps, is because it was discovered that this aspect of its orbit was calculated and reported on the same week of the Indonesian tsunami.
Now we need to talk about what that is. The Indonesian tsunami was Boxing Day 2004. What year were you all born? So this was just before you were born. On Boxing Day 2004, there was a massive earthquake in the ocean, and it sent a tsunami all over the planet, but in particular towards Indonesia, and 250,000 people died. 250,000 people died. It's by far the largest human disaster in the last 50 years that we had documented. Entire islands with people groups, with villages, when the rescuers got there, wiped clean like somebody had come with a scouring pad. They'd just been all taken out to the ocean. And so because of that, the discovery of this asteroid did not make page 1 or page 2 or page 10 or page 20. I get that.
Okay, I think it was end of 04 or 05. I forgot which of these 2 years it is. Same week. Odd thing is, of course, 200,000 people died in that tsunami. Odd thing is, if this asteroid hits in a place where it could hit, and I'll describe that in a minute, it will hit in the Pacific Ocean, it would create a tsunami in the Pacific Ocean that would make the Indonesian tsunami look like a street puddle that slightly overspilled its edges. So I think rightly the media attention was given onto the Indonesian tsunami, but that was not an excuse to then never have the press talk about this object. It's a real object. And there's something called the keyhole. It'll have a close approach to Earth in the year 2029, in April 13th, which, by the way, is a Friday.
You couldn't write that. It is true. April 13th, Friday the 13th in 2020. How old will you all be in 2029? Do the math. 23? This will make front page news then, because this football stadium-sized asteroid will be actually dipping beneath our communications satellites. It will be, Miguel, by far the largest, closest object we've ever seen in all of the time that humans have been observing the heavens. It will be by far the biggest thing that we've seen come this close. It'll make front page news then.
It will come close enough to Earth to dip below our orbiting communication satellites. For that passage, that will be the closest, largest thing we have ever observed in the history of our observing the universe. That's a shot across our bow. The uncertainty in its orbit at this moment is such that for that passage, there is a range of orbits it could have, which, if it goes through what we're calling the keyhole, Earth's gravity on it will be just right. Or rather,
Just wrong.
just wrong. That the next time around, it will hit Earth. 7 years later, April 13th. If it goes through the center of the keyhole, it'll hit the Pacific Ocean 500 kilometers due west of Santa Monica. It'll plunge into the Pacific Ocean to a depth of 3 miles. At that depth, it will explode, cavitating the ocean with a hole 3 miles wide, 3 miles deep. That impulse will send a tsunami wave that will basically wipe out the entire west coast of the United States and the east coast of Asia. Now, oceans don't like having big holes in them. So this 3 mile high wall of water does what? It's a hole in the water. What does it do? Falls back in the hole. This is not Moses here. We're talking... It won't just stay there, like in the movie. It'll fall back into the hole, slosh into itself, rise high into the air, fall back to the ocean, cavitate the ocean again. And it'll do this with such ferocity, it'll repeat itself about 50 times, taking about an hour. So every time it cavitates the ocean, it sends another tsunami. So it won't be just one wave like the Indonesian tsunami was. This will be 40 waves, 50 waves. Now, each wave has to pull back out to get ready for the next one. And it's separated by about a minute. So there's a limit to how far these waves will get on shore. We think it's about a 1/4 of a mile. So if you're more than a 1/4 mile inland, you can just watch this happen. If you're not, now, the $1 million Malibu homes, they will feel this first tsunami wave. And then that tsunami will basically pick up the homes. It'll bring them back out to sea. Then the next wave will come and return the home to the shoreline. But now the home is in a slightly different shape. And as this continues, all man-made objects along the coastline and trees and debris basically becomes this churning, ablative mass, wiping clean the entire coastline. Now, nobody has to die, because we'll know this well in advance. But I found there are two people who will die. There is the stupid surfer who says, I got to do that tsunami wave, dude. You know they're going to be out there. Okay? So we'll have dead surfers and dead weathermen. You've seen them. There's the camera guy over there. Come closer, watch the hurricane splash into the... Get this shot, can you see this? I'm reporting from the hurricane. Now, I'm a scientist. If this asteroid goes through the keyhole, there'll be people evacuating the West Coast, building shelters, stockpiling food. There'll be people praying to their gods. There'll be people doing all kinds of things. I'd rather be doing something about it. This is where engineers come in, and physical scientists, and physicists and astrophysicists. So, we've got top people right now working on a way to deflect the asteroid. Therein is the power of science. You don't have to build a shelter from something that could kill you. You can prevent the thing from killing you in the first place. It's like, how do you solve acid rain? Well, let's have acid rain-proof umbrellas. You know, no. You want to like stop the rain, all right? You know, how is your brain wired for finding solutions? So, there you have it. So we'll monitor the news at that time. By the way, it is not known who will pay for that deflection mission if it comes to pass. Probably America, but asteroids can hit anywhere in the world. And the UN, while there's a space unit of the UN, there's no funding stream. Suppose this were headed for Indonesia. Would we pay for that to deflect it? Suppose we pay to deflect it and we only half deflect it, and then hit somewhere else. That's an interesting geopolitical problem, you know. So it's not just fix it and go home, it's more complex than that. Oh, by the way, you got these guys who like stockpile nukes, and that community want to blow the sucker out of the sky. You know, there's the folks who want to use the nukes that we have. And the problem is, here in America, we're really good at blowing stuff up. We're less good at knowing where the pieces go after the explosion. Whereas when you deflect something, you can monitor your progress all along. But another question?
That was from about 12 years ago. Since then, we have much better data on Apophis. It's extremely unlikely that when Apophis does come by in 2029, which it will be, that it will go through the keyhole in such a way that when it returns in 2034, it'll hit the Earth. It's nearly zero. However, anybody been following the news the last week and a half? Because we found a new asteroid, so if you know what I'm talking about. And this is as of 10 minutes ago from SciMag News. It says, the asteroid 2024 YR4, that's what we're giving it the name, growing odds of impact. So let's see. It is between 130 and 300 feet in length. So not quite the size of a football stadium, but the size of a football field. And initial impact on December 22nd probability was above 1%. It's now up to 2.3%, and it's going up. So what does this mean? When you're older, please vote intelligently. Put politicians in positions of power that will actually follow science and listen to science, not pseudoscience, not stupid science, not ignoring science. Please don't put President Wormtongue, or whatever we're going to call the guy down south, in power here in Canada. We have an election coming up. Doesn't mean you have to vote for a particular party, but make sure your politicians are scientifically literate. Also, don't get your science from politicians. Get your science from scientists. You don't go to a politician for advice on plumbing. You don't go to a politician for advice on sewing. You don't go to a politician for advice on science. Go to scientists, please, for the love of God. I'm watching the events down south and just about wanting to throw up. There, I got political. Example 2. Ooh, new word. Geosynchronous satellites maintain their orbit over the same place on the Earth at all times, somewhere over the equator. What is the period of such a satellite? If you're able to stay in one place above the Earth, it means your period of the satellite will be the same that it takes the Earth to rotate. So here's the question. How many hours does it take the Earth to rotate? Jacob, get your calculators out, type in 24. We want to convert this to seconds. I think not. 24 times how many minutes in an hour? 60. Times by how many seconds in a minute? 60. Or you could just times by 3,600. How many seconds are there in 24 hours, Jacob? 24 times 60 squared. 86,000 what? On your formula sheet, what does it say the period of the Earth is? Does it say 86,400? It says 86,100. Mr. Dueck, are there not 24 hours in a day? It's way more complicated than that, and we will try and dive into it, but another day. For now, we'll use the value from our formula sheet. We'll say the period is 8.61 times 10 to the 4th seconds. By the way, the reason geosynchronous satellites are so nice, don't write this down. If this is the Earth and you have a satellite in geosynchronous orbit right there, it means anybody here can point their satellite dish and they know where that satellite is. There will always be a satellite in view. Now, the geosynchronous satellites all have to have the same radius, the same distance from the Earth, and it's such that pretty much about 70% of the Earth can see a satellite right around the, you know what, they're around the equator, Mr. Dueck, draw it properly. The geosynchronous satellite would be around the equator. Basically, most of North and South America, most of Africa, most of Europe, they can see satellites. It's a bit tricky at the Arctic Circle. It's a bit tricky at the Antarctic Circle, but it's otherwise a pretty good system. It means whatever satellite dish that you have, you can program it, and it will know where a communication satellite is, and that's not moving at all, because as the Earth rotates, it's rotating with it. Okay? Which brings us to the question. What's the radius of such a satellite? Ooh, good question. Declan, what are they asking me to find in part B? Radius. Ooh, is there a trigger word in this question, folks? That begins with the letter O? Is there a trigger word that begins with the letter O? Kevin M., what is it? Orbit. So what can I say? Declan, I can say gravity is what's pulling me in a circle. And now we're going to try and get an R by itself. It's going to be big G, big M, little m over R squared equals little m. And then I need to put the AC. Which version of AC am I going to use? Don't write this. I'm just putting it there as a placeholder. Which version of AC am I going to use? Oh, the period one. Yeah, because that's what I know from geosynchronous. Okay, so it's going to be, I'm going from memory. Is it 4 pi squared r over t squared? Do all geosynchronous satellites orbit at the same radius regardless of their mass? Yeah, little m cancels. That's good. Alrighty. Luke, talk me through it. I want to get the r by itself. So where is this r squared on the? Bleh. I think the first thing I'm going to do is I'm going to multiply it here, although there's already an r there, so it's going to be r squared. Or what's a better way to write r squared? R to the? Yep. Okay. I need to move the 4 pi squared over. How am I going to do that? Yep. I need to move the t squared over. How am I going to do that? We're doing our stuff moves diagonally, right? Yeah. So how? Times? And that gives me an r cubed. Final question, folks. How to get rid of a cubed, not square root, but yeah, let's write this out because it's kind of messy. I'm going to write r equals the cube root of big G, big M, t squared over 4 pi squared. Are we writing a test right now? Be stupid obvious, Luke. Say no. If we were writing a test, I absolutely would write out all of the numbers just to be really meticulous and careful. But let's see if we can go straight to our calculator. I'm going to type what's inside the cube root first, and then I'm going to go cube root answer button. So big G, 6.67 times 10 to the negative 11 times big M, 5.98 times 10 to the 24th times the period, 8.61 times 10 to the 4th. Don't forget the squared. I missed the decimal point, Mr. Dueck. And then divided by, I have to put the bottom in brackets, or you could have used your fraction button, 4 pi squared. I'm double checking for typos, Luke. I think I typed it in right. I get that, and then I'm going to go on cube root answer button. I got 42152615.6. See if you get that. They're pretty far out there, but even though it takes a lot of energy to get them out there because the rocket fuel, totally worth it. The idea of having a satellite that doesn't move at all relative to the Earth, so handy, totally worth it. When you hear about communication satellites, usually those are the ones that they're talking about. That's what we bounce most of our communication signals off, and that's enough to cover, I think it's something like 87% of the Earth. And the 13%, barely anyone lives there. It doesn't mean that we can't figure out a way to work around for them, but not enough for us to be freaking out. So I'm going to write it 4.22 times 10 to the 4.22 times 10 to the 7th meters, and I'll pause. Is there anybody that can't remember how to find their cube root button? This is your last chance to ask. And you should pick up how enthusiastic I am about the fact that you have a cube root button. I'm probably dropping a pretty solid hint here. Yeah, I don't get it. Okay, whatever. Is that all right? All right. Good. Yeah, good. Stretch out because we're going to a black hole, and then we're going to press pause. We'll finish with example 3. Jacob, did that work okay or not? It has an nth root. Yeah, so you do 3 nth root button. Yeah. That one is about 50-50. Some calculators have it, some don't. I understand what they're saying. Why would we need a cube root button when I've given you an nth root button? Yeah. Hey, let's go to a black hole. Suppose a spaceship is orbiting a black hole at an orbital radius of 8.8 times 10 to the 9th meters. The black hole has a mass of 6.8 times 10 to the 32 kilograms. Carson, what's A asking me to find? Why wouldn't it ever be asking me to find big G? Anywhere in the universe, maybe even inside a black hole, maybe not. That's the only, when I say everywhere in the, by the way, whenever I say anywhere in the universe, I should point out all of our physics breaks down inside of black holes. So I'm technically saying anywhere in the universe except on the inside of black holes, but maybe it could be, but we don't know. Anywhere in the universe. So little g. Now, because gravitational field starts with an F, don't write this down, a lot of people do this. Oh, I should say I like this question, I like this question, I like this question. I do not want gravitational force. There is enough information there that you can find the gravitational force, not what I asked for. What did you say? What symbol was it, Carson? And the equation that I gave you on your formula sheet is that. Yes? What I'm saying is, if you take the gravity equation, big G, big M, little m over r squared, and you cancel out the little m, that's your equation for gravitational field strength. And I did that on purpose to show you how they all relate together. I deliberately did not give you an equation plug and chug for little g. So it's going to be big G mass. I've scrolled, oh no, there, it's 6.8 times 10 to the 32 over r squared, 8.8 times 10 to the 9th. Don't forget the squared. What's the gravitational field strength at this location? I got a typo there. 6.8 times 10 to the 32 divided by 8.8. Scientific notation button 9 squared. I got 586. Carson, units. Oh, this very much has units. Please look at the units right from the equation. What's on the top? What's on the bottom? Newtons per kilogram. This is also meters per second squared because it's sitting exactly where acceleration would in our F equals what. So if you said meters per second squared, I'd mark that right. But generally when we're talking about gravitational field strength, we refer to it as how many newtons of force on every kilogram. Would this be fatal to those on board the spaceship? Why or why not? Why would this not be fatal? In fact, why would the astronauts not feel it at all? No, they're not dead. Wow! No, they're not in a black hole. They're outside of a black hole. It's orbiting around a black hole. I just gave you the key word. What's the trigger word? On the ISS, are the astronauts in Earth's gravitational field? Yes or no? Do they feel it? No, they're floating. Why? Because they are in, and when you're in orbit, you are in, now I'm looking for two words, each one starts with an F. Free fall. In orbit, you'd be in free fall. In fact, you could probably, Carson, because you'd be coming into this black hole in partial free fall. As long as you did it carefully, you'd be in partial free fall. You could probably keep the G's low enough that you could survive, and then while you're in orbit, you'll be fine. The tricky part would be exiting, because exiting, you're going in, I'll call it negative free fall, which doesn't quite make sense. You're going against free fall. You're definitely going to have to be pulling more than 1 G, but if you spread it out over a few years, you could still probably pull it off. It just wouldn't be very comfortable over a few years. But certainly, let's suppose we had Star Trek technology and we beamed them into orbit right here. It'd be fine. It'd be fine. No, in orbit, and you can put in brackets, free fall. Right? All right. Let's suppose they want to leave and get out of the black hole's gravity well. And again, you're correct. The reason I know, by the way, that they're not inside the black hole, when we find the escape velocity for part C, Carson, it's going to be less than the speed of light. I made sure of that when I crafted this question. Did I say I like this question? I like this question? I did. Okay, good. Sophia, what's he asking me to find? Should be called escape speed. I've done that rant on purpose because that tells you you want to use conservation of energy, G. I'm going to start some of my work up here because I got some white space room. I'm going to write out the law of conservation of energy right here first. And what was weird about escape velocity speed was, what did we want the final potential energy to be, Sophia, if we wanted to make it all the way out to infinity? And we wanted to do it so perfectly that when we got to infinity, we came to a stop, which means what's our final kinetic energy exactly as a number. Yeah, this was the derivation. Now, you may have memorized the escape velocity equation. If you've done that, I'm fine with that. But if you blank, or if, like me, you hate memorizing stuff when you can just derive it, now I can say, okay, it's going to be a half mv initial squared plus mgh. No, no, negative big G, big M, little m over r initial equals 0. Ragav, what did I usually do next? What would you do next if you're making this equation look prettier? I would that you can cancel out the little m's right now. I'm going to do that on the next line. I just don't like the way this is written. I think the first thing I would do, Ragav, is I would plus this to that side, because then I have a half mv squared equals positive big G, big M, little m over r. And yeah, the m's cancel. Both the V and the R are initials, so I got sloppy and didn't bother putting the I's because they are what they are. We want to get the V by itself. Sophia, how would I get the V by itself? I'm going to times by 2, and then that gives me a V squared. So, yeah, V is going to be the square root of 2 big G, big M over R. You know what? Normally I would write out the numbers, but I just noticed on my calculator right now, I have big G, big M over R squared. Sophia, I think if I backspace and just put a 2 times in the front and delete the squared, I can hit equals and then go square root answer button. And that's how I would do this question. Absolutely, Declan, I would save myself some typing and save myself some typos. I'm going to go boom, and then I'm going to go square root answer button. Carson, did you get an answer less than the speed of light? Yeah, I know you're working on it. I think you're going to get something in the 10 to the 6th range, I think. Yeah. I got 3.21 times 10 to the 6th. What's the speed of light? 3 times 10 to the... Yeah, this is about 100 times slower than light, so still doable. I mean, you need a lot of energy, and this is currently beyond our technology, but let's assume if we're orbiting near a black hole, our technology has advanced. But Carson, you've raised a question, because initially you had suggested that they were inside the black hole. Let's pretend you're an astronaut on this spaceship, and for the science of it, you decide to jump from the spaceship and plummet into the black hole in your spacesuit. Let's pretend you do it like you're cliff jumping. So you're going to go pencil-shaped feet first. What would you experience? At first, it wouldn't be too bad because you're in free fall. You wouldn't be feeling the gravitational pull, but there would come a point when the gravity field was so strong that the difference on gravity between your feet and your head, just that small distance, it would be different enough that it would feel like your feet were being tugged down compared to your head. It would feel like you were getting stretched a bit. And at first it would feel pretty good. Because when you wake up in the morning, most of us, one of the first things we do is we stretch ourselves. But as you kept falling, suddenly it would feel like one of those medieval torturers' racks where you may have seen where they strap the person's arms above their head and they strap the feet down and they start turning a wheel and it starts pulling them apart and apart. And in fact, after a while, very quickly, in fact, what would happen is the difference of the tug between your feet and your head would be stronger than the molecular bonds that hold you together. And you would bifurcate. You would split in half, probably right around your belly button. And now there'd be 2 of you, and your little adventure would be over. But then those 2 pieces continuing to fall would bifurcate as well. And there'd be 4 pieces, then 8 pieces, then 16 pieces, then 32 pieces. But not only that, as you got closer and closer and closer to the black hole, it would start affecting the very curvature of space-time. Space-time itself would be so curved that you would find yourself being compressed and extruded like toothpaste through a toothpaste tube. In fact, you would end up as a single stream of molecules, no, a single stream of atoms tunneling your way down to the black hole. And we have a name for that process. Does anybody know what word physicists have invented to describe falling into a black hole? You might know the word, Carson. This is called spaghettification. Yes. There's your word to take home today at the dinner table. What did you learn in school today? Actually, mummy, I learned that if I fell into a black hole, I would get spaghettified. Oh, actually, you were ever so clever. So if you saw the movie Interstellar, at the end of it, sorry, spoiler alert, Matthew McConaughey goes into a black hole. Almost certainly he would not survive without some pretty severe intervention. Okay. We're going to pause here.